talk about estimation, and this is going to be, I have a fair amount of slides, but I think I'm not going to spend much time on them. So I made a statement that might have seemed a little bizarre, which is I said that testing and hypothesis testing and confidence intervals for the single included endogenous regressor problem in IV are solved problems, and we have essentially something that's uniformly optimal, which is really unbelievable. But estimation is really hard, and we don't know how to do it. So how can that be? Well, so let me pose the question to you. Suppose that you have, again, go to the bound example of an irrelevant instrument. Can you construct an unbiased estimator? And the answer is no, you can't. You can't construct an unbiased estimator. Because the estimator can't, because it's totally unidentified, the distribution of the estimator can't depend on the true value. So if the distribution of the estimator, right, because it's totally unidentified, that's what we mean by totally unidentified. The distribution doesn't depend on the true value, the distribution of the data doesn't depend on the true value, the distribution of the estimator can't depend on the true value. So I've got an estimator that's got some distribution. I can pick my true value wherever I want. Right? So it's not going to be unbiased. It's not going to be median unbiased. So to come up with, it's not really going to be a good research program to say I want a uniformly optimal estimator uniformly in mu squared, because we know that there's not going to be anything with any optimality. For point estimation, there's not going to be optimality problems. The thing about interval estimation is that we know in the unidentified case the right answer is minus infinity to plus infinity, but in the unidentified case for point estimation, there isn't. I mean, I suppose you could randomize, right? You could go to some estimator that devolves to be 51. You flip a coin, half the time you say minus infinity and half the time say plus infinity. And then that's going to be, in some sense, unbiased if you can average the infinities. But that's not the world's best estimator. Okay. So the whole challenge here is to come up with estimators that do better than two-stage least squares. It turns out two-stage least squares is just about the worst thing you can do for estimation and for hypothesis testing. So there's a whole family of things that these guys back in the 60s and 50s invented called K-class estimators. Limmel's one of those, which is it's the smallest root of the certain determinantal equation. There's something called Fuller K, which you saw in the Yogo table, which is you take Limmel. Limmel doesn't have any moments, so if you do a little modification to it, you subtract off a small number, then that makes it have moments, and some guys proved that a long time ago. And so there's been some simulation studies. Because of these problems of weak instruments, there's been more interest in this problem. There's been a fair amount of simulation work. There's a very nice paper by Hahn, Hausmann, and Kirsteiner that does a big Monte Carlo study. Back when these guys were doing it, Anderson and Kunitomo and Moramoon and Rothenberg and this group that was these people that were doing it back in the 60s and 70s, they essentially just had to use algebra, and their Monte Carlo studies were extremely limited because of the computational resources at the time. So Hahn, Hausmann, and Kirsteiner did a really nice study. They seem to think that this Limmel K estimator works pretty well compared to some of the other things. Let me give you my opinion on this, and I'm going to emphasize that this is just my opinion. My opinion is that the point estimation, I'm just not a big fan of point estimation in this problem. And I'm much more interested, I think that the interval estimation is a more useful device. Basically, the point estimators can have quite strange properties, a great degree of bias, really large tails, whereas these confidence sets have really quite well understood properties that and nice theory associated with them. If you want to report a point estimate, Limmel has some nice features, which is that Limmel is going to always be in the Anderson-Rubin confidence interval, and it's always going to be in the CLR confidence interval. I should mention something, which is that Limmel, turns out, I guess I didn't write this down, Limmel has another nice, Limmel has another nice feature, very interesting feature. This is a non-obvious feature, which it turns out that Limmel minimizes the Anderson-Rubin statistic. So if you did the exercise where you're doing this hypothesis test, you take y minus cap y beta naught and regress it on z, and you do that again and again and again and again, and you get all these f statistics, and then you find the minimum of those f statistics, and you take the value that minimizes those f statistics. That's the Limmel estimator. So it's necessarily going to be in the Anderson-Rubin statistic if the Anderson-Rubin statistic is non-empty. And it's also going to be in the CLR, the CLR confidence set. Okay. Bootstrapping. I'm going to spend just a short time on this. Bootstrapping and sub sampling. So just to be concrete, here's a bootstrapping algorithm. So you estimate beta by two-stage least squares, and you estimate pi just by the first stage OLS. And then you take the residuals, u and v, the residuals u hat and v hat, and then now the way the bootstrap works is what you do is you resample from these residuals to compute fake data or artificial data, resampled data. All right, so you're going to take the u hat and the v hat, and the estimated pi hat and the estimated beta hat, and you sample at random with replacement from the residuals, and you create some new artificial data, y tilde and cap y tilde. And then with your new artificial data, you're going to do two-stage least squares. And then you do that again and again and again, and then you build up a distribution of two-stage least squares estimators. And t-statistics. And if you build up a distribution of two-stage least squares t-statistics, you could take the critical value of the bootstrap distribution and you could apply that to your actual data, for example, to the t-statistic computed in the real data. So the problem is that this doesn't work. Okay, so in fact, you can prove that this doesn't work. So under strong instruments, it does, and you can prove that. And under weak instruments, it doesn't, and you can prove that. And the reason is that, I guess one way to say the reason it doesn't work is that for this bootstrap to work, if you think about what's going on, you would need to have pi hat being consistently estimated. But under weak instrument asymptotics, pi hat isn't consistently estimated. And moreover, the distribution, essentially what you'll be simulating, here's one way to say it. You get the pi hat in the data. Pi hat in the data is going to imply a non-centrality parameter mu hat based on the estimated pi hat. You're going to be bootstrapping a sampling distribution that's based on the empirical non-centrality parameter based on the empirical pi hats. The problem is that empirical pi hat, because this F statistic doesn't equal the non-centrality parameter, it's a random variable around the non-centrality parameter, that those pi hats don't equal the true pi's, and the delicacy of these distributions is such that you'll get the correct bootstrap distribution around the wrong mu hat, around the wrong mu. It'll be around mu hat rather than around the correct mu. Now you say, oh, that can't make a big difference. Well, that's just a quantitative question. Either it makes a big difference or it doesn't, and so you do a simulation, and it turns out it does. And the reason it does, especially for two-stage least squares, is because you saw what that two-stage least squares t-statistic distribution looked like. It was insane. So it turns out that it depends delicately enough on mu that if you simulate it around the wrong point, you're going to get the wrong critical values, and it can work quite poorly. It turns out there's another thing called resampling. So there's a really nice paper that goes through all of this, a couple of them by Morera, Porter, and Suarez. You can read all that. They have a way to make the bootstrap work to give second-order improvements in, for example, the Anderson-Rubin statistic, but I'm not going to deal with that. There's another thing called resampling. Resampling is some modification where you don't actually estimate the pi's, and instead what you do is you take a little subsample of the data. So if your full data set is like 400 observations, you might take the first 30, and then a window of about 30, and then you slide through if it's in time series. And for each of these, you would compute the two-stage least squares estimator. And now you've got some scaling problem because you started with 400 observations and you're only using 30. But if everything is going to be approximately normal, the scaling factor is going to be square root of 30 divided by 400. And then you can get an approximating distribution. And sometimes that works. In fact, in many cases that works, and it doesn't work here. And the reason it doesn't work here is that the non-centrality parameter that you're going to be looking at is a non-centrality parameter for 30, but your actual estimate is based on 400. And so you've got the wrong non-centrality parameter. It's the same problem, the same reason the bootstrap doesn't work. You're going to be getting a good estimate at the wrong place. Right? So, and it turns out, does it matter or not? It's numerical, and it does. And so there's a couple of papers by Andrews and Guggenberger that go through all of that stuff. Bootstraps don't always work. Okay, so let me shift gears here and talk a little bit about GMM. So everything so far has been talking about IV regression. So for a group of time series economists, none of that is probably directly relevant, a little bit of it maybe. But actually it turns out all of it has analogs here, and it's just easier to talk about it there. Okay. Let's do some GMM basics. Okay, so GMM is you've got some first order condition type thing here. So in the linear case, that's just going to be y minus cap y times beta. There's a true parameter value. You've got some instrument z. The orthogonality condition is that the expectation of the error term, and in this case it's a g-dimensional equation times the instruments, is 0. So you form this big vec thing that's gk by 1, and those are the moments that you're going to take, that you're going to evaluate, and you're going to use them to estimate this unknown parameter theta. And the way you do it is by constructing this big vector, and you have some weighting matrix, and then you minimize this GMM objective function to get the GMM estimator. The GMM estimator, there's a lot of flavors depending upon how you construct the objective function, given whatever moments you happen to have. In the linear case, this is just y minus theta prime yt, and this is just going to be, for the right estimator here, this is just going to deliver two-stage least squares. The right weighting matrix, it'll just deliver two-stage least squares. So that's GMM, right? So that should be completely familiar. Okay. So I'm going to go through the large sample distribution theory of GMM. I'm going to do so in a way that is not completely standard because it's going to lead into how I'm going to talk about weak identification in GMM. So let me introduce a few things here, which is, first of all, I'd like to introduce this idea of the centered sample moments. Okay, what in the world is this? So phi t, remember phi t from the previous page is the errors times the instruments. So the centered sample moments, then, this thing is going to have mean 0 at the true value theta naught. That's the identification condition in standard GMM setup. For some wacky reason, I'm actually subtracting the value here. This expectation is 0 at the true value, theta naught, but I want to carry this along for other values of theta 2. Usually we don't have to do that. Usually we don't have to do that because all GMM asymptotics in the standard case is local, so all that matters is the true value. But in the IV case, remember, two-stage least squares wasn't consistent, so I'm not going to be able to restrict myself to local asymptotics in the GMM case. So I'm going to drag along this mean and look at this deviation right here. All right. Then anyway, if you want to think about it at the mean, that's fine, and then it's going to have some covariance matrix. And the version of the slides says typos in there, which is GMM. Efficient GMM, I think, in your slides is upside down, or efficient GMM is inefficient GMM, I think, in your slides. I think there's no inverse in quite a few of your slides, but not all. Is that correct? Is the version of the handout? Yes, okay. Sort of a test, I guess. A test of myself, I guess. So the efficient GMM is you take this covariance matrix and you use that as the weighting matrix. That's 2 pi times the spectral density of the moment condition at frequency 0, which was introduced this morning. I'm not going to go through estimation of the spectral density matrix. That's Mark's going to talk about that on Wednesday morning, in the first lecture on Wednesday morning. Okay, so but it's the usual thing. It's just like Nui West, if you want to do it that way. Although we'll suggest some reasons why that might not be the best way to do it. So this is Nui West. And so that's going to be efficient GMM. Efficient feasible GMM is you could do it in a number of different ways. you could, for example, do a two-step, and you could just start at an identity matrix or some fixed weighting matrix. You then use the parameter values estimated in the first step to compute the weight matrix that you would then use in the second step. You could iterate that, so you could keep on going. All right, so these are two efficient GMM methods. Another efficient GMM method is to use what's called the continuous updating estimator, which Hansen, Heaton, and Rohn introduced in 1996, which is kind of interesting because what you do, it's much more tedious than this. This is pretty easy. You get a theta hat, you evaluate the weight matrix, and then you find another theta hat and evaluate the matrix. Here you have to evaluate the weight matrix at every value of theta, and it sort of seems like more of a moving target. Now, in terms of first-order asymptotics, it's not going to make any difference. All three of those are first-order efficient, and they're all going to be consistent. So to establish consistency, just to remind you of that, what you want to do is you want to argue that the objective function is going to be such that as the sample size gets larger, it's going to be crunching down into a steeper and steeper objective function, so the probability of being outside some range is going to be increasingly small. So that, in fact, within some epsilon window, the probability of being inside that, of the peak of being inside, of the estimator being inside that, goes to 1. So that's the consistency argument. Once you've got consistency, perhaps at a suitable rate, you can then take a Taylor series expansion, and then because you're only local, you know you're going to be in this neighborhood, the Taylor series expansion can be made such that you're just evaluating the derivatives and the second derivatives at that local point, and then you get this approximation to the objective function. So the approximation to the objective function works by the objective function getting tight and being approximately quadratic. If it's approximately quadratic and if it's tight, centered around the true value, then we're going to have an approximately normal asymptotic distribution, and that's the essence of the standard GMM derivation. And so you just work out what those terms are, and you get the usual thing. This should be completely familiar, although this derivation might not be exactly the derivation you're used to. Usually the derivation works from the first order conditions, but I don't want to work from the first order conditions. I want your intuition to be developed not from the first order conditions, but from the objective function. Because what's really happening, what has to be happening, is that objective function has to be going like this and getting quadratic up there. And I'm going to suggest that's not a good approximation for IV or GMM with weak instruments. And that's the essence of the problem, why this is going to provide a poor approximation. You know, I say this will provide a poor approximation. We already know it is. A special case of GMM is the linear IV regression model, in which case efficient GMM is two-stage least squares. So that's if that the two-step two-step. Efficient two-step GMM is two-stage least squares, and we already know in the two-stage least squares problem this doesn't work. So it stands to reason that once you start throwing in a bunch of nonlinear stuff, it's not going to work any better. Somehow the nonlinear stuff isn't going to compensate for the weak instruments. Okay. Okay. Minor terminology. Weak identification instead of weak instruments. I think weak identification is a little bit more general phrase. Weak instruments really thinks about instruments' correlation between X and Z, and you don't really have a Z in the general GMM setting. In fact, whatever the Z is going to change depending upon where theta is. So weak identification is maybe a better way to think about it. Okay. So I think I've already said this. If there's weak instruments, there's a couple of problems. And one, the curvature, one of the problems is they're not well approximated by a normal. It turns out that this derivative here isn't going to be well approximated by a normal with mean 0. And you can see that in two-stage least squares. Here's the two-stage least squares objective function. And so this is exactly quadratic. So certainly the quadratic approximation is a good one in this instance. So it can't be that the real problem is failure of the quadratic approximation. It's got to be a little bit more than that. So this is an exact quadratic, and now I've just expanded this out. And so this expansion corresponds exactly to that general Taylor series expansion, except there's no remainder term here because it's it's exactly quadratic. Okay, so what's going on is twofold. First of all, the curvature, this thing here, is small. Well, what is this? This is cap y prime pz cap y. Well, that should ring a bell. It turns out the curvature in the two-stage least squares objective function in this GMM's framework is proportional to the first-stage F statistic. All right, so that's that first-stage F statistic showing up again. Let me see if I don't have the expression. So the first-stage F statistic, the curvature is proportional to the first-stage F statistic times the number of instruments and then just the variance of the error. So the bigger the first-stage F statistic, the more curvature there is. The curvature matrix, what that says also, remember if mu squared is small, what's going on here? If in this usual asymptotics, this thing is converging in probability to something, to this, converging in probability to this. But this is the first-stage F statistic, and if mu squared is small, it's not going to be well approximated by something that's non-random. Right? So this thing is actually, in the weak instruments case, going to be random. Well, how about this? Is this going to be normal? Well, no, it's not. It's not going to be unconditionally normal. It's going to be this object right here, and we looked at that, in fact, in the weak instrument calculation we did at the very beginning. This is the numerator term, and this is the denominator term, and remember how that numerator term had that lambda plus zu prime zv, or lambda for zv prime zu expression? So that actually is some fairly complicated object. And conditional on this, it's actually got a mixture of normals distribution. Or this actually has a mixture of normals distribution. It's normal conditional on this. So everything is messed up here. This approximation says that we're going to approximate this as being normal with a non-random variance matrix, and we're going to approximate this as being a constant. Well, in weak instruments, this is the F statistic, basically, and this is some messy thing that's got some funny mixture of normals distribution that's not even centered properly. So the problems with the two-stage least squares, so the whole problem with the GMM is going from here to here and going from here to here. And so we need to have a different framework for thinking about GMM. Okay. So what are the alternative approaches? But by the way, there's the Hansen, Heat, and your own paper did a really great job of documenting the problems of some of the strange features of the GMM estimator, and how. So what did they find? They found that in a Monte Carlo study that was calibrated to a couple of different empirical problems, that the two-step GMM converged to a different. Was it the iterated GMM and the CUE and two-step GMM all gave different answers that were quite different. The distributions were centered in funny places. T-statistics didn't reject 5% of the time. Confidence intervals didn't have the right coverage. There were all these very strange features that were quite troubling. And that makes sense in the sense that they're all, when you look at it from this sort of weak instruments perspective. Well, again, we have the same possibility of doing a variety of different approaches. You could try finite samples, but since there's no way. You could try Edgeworth, but that wasn't the right approach in the simpler problem, so it's not going to be the right approach in the more complicated problem. Bootstraps and resampling, they're not going to work here either, so you're left with dealing with something else. And so here's another nesting that works, and this gives some results. So this nesting is just an extension of the weak instrument asymptotics nesting that gives some tractability and gives a framework for thinking about asymptotic robustness of different procedures. And essentially, what the device is going to be is exactly like this nesting of pi over the square root of t. But instead, what we're going to do is we're going to think about the expected value of the GMM moment function not exploding. So one way to think about what makes GMM work in the usual setting is that if you move a little bit away from the true parameter value, the expected value of that moment function gets so out of control that your that you're going to be driven to be near the true objective function. Once you're in that local neighborhood, then everything, and you have a steep objective function, you're going to be in good shape. So we need to break that link, because that's the link that's not working. And so the way to break that link is the same way as to break that link with the pi over the square root of t, or pi over the square root of t approximation, or c over the square root of t approximation, and that's to allow this thing, root t times this GMM objective function in expectation, get converge to a constant. So that's just the analog to the pi over root t, or pi times square root of t approximation. Okay, so where does that take us? If I now look at this, these moments, t to the minus 1/2 times the moments that we're working with in the two-stage least squares case, I can just, it's nice to work with that example because everything can just be done explicitly. I just rearrange, so I'm going to now write yt minus theta naught y is just u, and then I'm left with theta minus theta naught times y. And so then I can break this up as to be u times zt, and this is going to be very well behaved. That's just going to be a central limit theorem, u times zt, plus something else, and that something else is going to be theta minus theta naught prime y times zt. And so this is explicitly what this first term is, this psi t, which is going to be phi t minus its mean in this expansion for the two-stage least squares estimator, plus then this non-random bit, and this non-random bit is something that involves the strength of the relationship between the instruments and the estimators, and the instruments and the included endogenous regressors. This thing is this part here is going to be super well behaved, and it's going to obey a central limit theorem, and that's going to be a good approximation even with a reasonably small sample size. The trick is that this mean function here is going to be non-random, and it's not going to be increasing quickly. That is, we're going to look at it in a local neighborhood, and in fact, it delivers exactly the right local neighborhood if you have, in this linear case, setting a pi to be c over the square root of t. So, putting all of these pieces together, in general, what we'll be doing is we'll write the moment function, this sample average of the moment function with the square root of t normalization, in these two bits, the part that has mean 0, now for all values of theta, and this is why I've included this additional thing that I was mentioning at the beginning of subtracting out all values of theta, plus then the mean term. And so these are these two terms, a mean 0 piece and then the mean term. Okay, what does that give us in terms of asymptotics? Well, this mean term here, we're just going to posit that this thing converges to some limit uniformly in theta. And that's going to be the modeling device that will deliver this other non-standard asymptotics. This term here, this psi t of theta, well, in the two-stage least squares case, this was just going to converge to a normal. More generally, this psi term here, which corresponds to this term right here, is something called an empirical process. What is an empirical process? An empirical process is some function of the data like this that has mean 0 that's indexed by something, and here it's indexed by a parameter. And this looks like something that should obey a central limit theorem, and it does. It's going to obey a central limit theorem at any particular value of theta. This thing's going to obey a central limit theorem. We're actually going to model this, or assume that it does so at every value of theta, and in fact, if you put together all those values of theta, it's going to obey a functional central limit theorem. So this thing is going to converge to a Gaussian stochastic process on the parameter space with mean 0, and then a covariance function that's given by, this should be subscripted theta 1 and theta 2. So that's a typo. This should be theta 1 and not theta t. This is the covariance. A Gaussian stochastic process, a Gaussian process, a Gaussian random variable. A normal random variable is characterized by its mean and its covariance matrix. A Gaussian random process is characterized by its mean, which in this case is 0, and its covariance function, which gives the covariance between the process at one point and another point. Those points are supposed to be in the slide, theta 1 and theta 2. They are theta 2 and theta t, and subsequently nothing at all. Okay? Okay. Let me talk a little bit about this. So this goes in the category of complete digressions that are good for you. So what's a Gaussian stochastic process on theta? You saw the functional central limit theorem this morning, right? You saw the functional central limit theorem this morning, and the functional central limit theorem said that if I consider some function psi sub t of tau, which is going to be a partial sum of these epsilons from 1 to capital tau, this is actually a function on the unit interval. All right, so tau runs between 0 and 1. So this is in this terminology an empirical process. It's a mean zero function that's indexed by this parameter tau, and so it's a mapping from, in this case, from tau to the space of, well, if I made this connect the dots, continuous functions. This obeys a functional central limit theorem. A functional central limit theorem is what we need here, and the only difference between that empirical process and this empirical process is that this is well, there's a couple of differences. First of all, this empirical process is indexed by a scalar, whereas that one is just some general higher dimensional vector, but that shouldn't stress us out. And the second aspect, which is a little bit interesting, is that this empirical process has a very specific covariance matrix. So the covariance matrix for this empirical process, if I pick two values of this empirical process, psi t at tau 1 and psi t at tau 2, this has a very specific covariance function, and that's going to basically be the minimum of tau 1 and tau 2. Right, so that's the covariance function for a Brownian motion process. And so that's the covariance function here. There's a covariance function over here, which is this thing that I did with the wrong subscripts. At theta 1 and theta 2, that's going to be its covariance function. It's not going to have this particular covariance structure. It's going to have some other covariance structure. But otherwise, it's completely parallel. At any particular point tau, this thing is going to be normal. At 2 points tau 1 and tau 2, it's going to be jointly normal in the limit. At any k points, this will have a joint normal limiting distribution at any k points. Same thing here. I could slice this at any k points, any k thetas, and it's going to have a joint normal limiting distribution. And this is going to be its covariance function. All right, so what are the two things we need to prove that this works? The first thing that we need something called, and I think Mark mentioned this morning, which is convergence of finite dimensional distributions. The convergence of finite dimensional distributions says that if you take this process and you slice it at any k points, you cut it, take any k values of it, that's going to converge jointly to a normal distribution. Right? That clearly is going to be the case here. I could slice it at 2 points in time, and it's going to converge to a joint normal. Same thing here, same thing here. The second thing we need is something called tightness. So if we can characterize it at any finite number of k points, that means we can come very close to characterizing the distribution of the process over the whole thing, but not quite. We need something that's going to help us connect the dots. So I can get 2 points that are very close to each other, but how am I going to bridge that in between? Well, I'm going to need some sort of continuity or what's called stochastic equicontinuity or something like that that's going to allow me to make sure that I can carry that distribution from here to the distribution to here. And so that's this condition called tightness or stochastic equicontinuity that entails going from a distribution on very many but finitely many points to the distribution on the function. And that's really, actually, this is the hard part of functional central limit theory, and so there's books on that. Okay, so What that means is that this object here converges in a functional central limit theorem sense to a stochastic process defined on the parameter space plus a mean process on the parameter space, and that makes sense. It makes sense that this thing is going to have a normal distribution that doesn't blow up. If it were blowing up, it would mean that the instruments are strong. All right, so if we put this all together and we assume that the weight matrix has some limit, then this is that the objective function is going to, well, what? It's going to converge to a chi-squared type process on the parameter space. So it's going to be a random process on the parameter space. Now, this looks a bit much, but in fact, this is just a natural, I think, extension of what the two-stage least squares calculation did. And in fact, all of this, if you follow through all of this, and if you take derivatives of this objective function, for example, you get the limiting distribution of the two-stage least squares estimator that we did back at the beginning. So this just generalizes this two-stage least square stuff. All of the findings in the usual weak instruments asymptotics apply here in the sense that you don't get consistency, you have non-standard limiting distributions, J statistics don't have the right chi-squareds, standard errors aren't meaningful. But all of this is exactly what Hansen, Heat, and Yaron found. Okay. So that gives us the tools that we need to start analyzing the problem. All right, so now this is completely parallel. How would you detect weak identification? This is actually unfortunate. So this is a good research project. Okay, this is a good research area. Unfortunately, there aren't good tools for this. I'm going to give you a couple of ideas. I'm going to give you some basically kind of lame ideas. Okay? So lame idea number one is you can always just look at the first stage F statistic, but the trouble is it doesn't really mean very much. And here the reason the first stage F statistic was useful is that its mean was the concentration parameter. Unfortunately, if I look at a robustified first stage F statistic, its non-centrality parameter is no longer the concentration parameter that's relevant for the distribution of even in linear GMM of the IV estimator, the Gmm Estimator. Right, so the link between the first stage F, the tight parametric link between the first stage F and the distribution is no longer there, and so there's work to be done. So I don't have an answer to that. That's a good project. All right. You can look at it. I mean, if it's 70, I guess that's probably a big number. I have no idea what 10 means. If it says 10, I don't know what that means. Another thing you could do is you could use Wright's test. So what Wright does is he essentially uses a version of the Cragg-Donald statistic, and this works in the nonlinear case. So this is not recommended. The problem with this test, is twofold. First of all, this is looking at the local curvature of the GMM objective function. There's two problems. One problem, and this is an important one, which is in the GMM case, in the general GMM nonlinear case, the objective function doesn't need to be single peaked. So the objective function could be like this, right? In the general nonlinear GMM case. In the IV case, it was nice and quadratic, but that's not necessarily true in the general nonlinear GMM. So any analysis that you do about the local curvature around the GMM estimate is only telling you a little, whatever it tells you, it's only going to tell you something about what's going on right there. In weak identification, it's a global problem. And in fact, I don't know if I'll get to this, but there's an example in one of these consumption cap M things where you construct an Anderson-Rubin confidence interval for for the coefficient of risk aversion in the CRRA utility function problem, and you get two values. You get two confidence sets, and one is centered around 2, and the other is centered around 40. And this literature says, right, you can reconcile the one way to reconcile some of these equity premium puzzles is by having incredibly risk-averse people, and you actually see that in terms of a double dip in the GMM objective function. So that's a potential problem of the right procedure, which only looks locally around the GMM estimator. The other problem is that actually this is a test for non-identification. The issue is not non-identification, but weak identification. Now, the thing is, the test uses some bounding procedures, so it actually uses a really conservative critical value, so it has very little power against small departures from non-identification. So in practice, it seems to work okay, but I'll tell you, the theory is not really what one would like. So for those of you, for the graduate students here who are trying to find a good theoretical econometrics problem, this is a good problem to work on. Here's some symptoms. So if you run if in your analysis you do GMM and you do two-step and you do iterated and CUE and you get 3 really different answers, that's a really bad sign. Okay? That's a bad sign. So that's an indication that something is going on. If you can plot a concentrated objective function, and you know that's another sign that things are not working well. Okay. Unfortunately, there's not a lot of tools there. Let me talk about hypothesis tests and confidence intervals, because there are some procedures here that are useful. All of that setup of that Gaussian stochastic process stuff has a payoff here. And the payoff, or part of the payoff, is in noticing that at the true value, this is a typo. This should be theta sub naught. At the true value of, let me back up. I'm going to back up. All of that work setting up the Gaussian stochastic process has a payoff, and here's where the payoff is. And I want you to look at this particular objective function, which is something called the CUE objective function. So this is the Hansen-Heat neuron continuous updating estimator objective function. The thing that's interesting about this objective function is that instead of being iterated or two-stage, we're evaluating the weight matrix at the same point as we're evaluating these moments. Right, so remember, this weight matrix is the hack estimator, and it's the hack estimator that's based on basically the outer product of these things. Right, so the weight matrix is evaluated using the optimal GMM weight matrix at the same points. The numerator and the denominator evaluate the same points. That's what we saw in the Anderson-Rubin statistic. The numerator and the denominator were evaluated at the same points. The CUE objective function is the GMM analog of the Anderson-Rubin statistic. And in fact, suppose that I'm evaluating it at the true, suppose that this is evaluated at the true value. The CUE objective function evaluated at the true value is actually going to be chi-squared. Well, why is that? At the true value, this Gaussian stochastic process is normal, but there's no mean part of it because it's the true value, so the moment condition holds. So this is a normal. And this is a normal. What's this? Well, it's at the true value, so there's nothing fancy about this. This is just a hack covariance matrix estimator at the true value. It's just going to be what it is. Well, what it is the covariance matrix of this guy. So it's chi-squared. And so at the true value, the CUE objective function has a chi-squared k limiting distribution. And that's robust to weak instruments. I didn't say anything about strength of instruments anywhere. That's the true value. So that's exactly the same story as Anderson-Rubin. So we can actually think of the CUE objective function as the nonlinear extension of the Anderson-Rubin statistic. So actually, that's what I call it. I call it the nonlinear Anderson-Rubin statistic, or the GMM Anderson-Rubin statistic. This insight, there's this really great paragraph and table in a paper by Katra Lakota in 1990 that had this insight that was just totally missed. It was lost to the world, as far as I can tell. but this was figured out quite a while ago. Okay. So what that says is you can test. You can come up with a. You can do a test that's valid asymptotically, no matter how strong the instruments are. That is, it'll have the right size by just evaluating the CUE objective function and comparing it to the chi-squared k critical value. You can also construct confidence sets. And so the way you would construct confidence sets is by considering the set of values of theta for which you fail to reject using this GMM Anderson-Rubin statistic. And that's going to be a valid 95% confidence set for the true parameter values. And that's true no matter how strong or weak the instruments are. I should mention that this has the same interpretation issues that the Anderson-Rubin statistic does. So it could be, in some sense, at the true value, but if your instruments are invalid, then you're going to be rejecting. So it has this interpretational problem. It's subtlety. I guess problem isn't the right word. It's just something you have to be aware of. Okay. And this just goes through the algebra, saying that this is in fact in the GMM. Excuse me, in the linear IV problem. This is just the Anderson-Rubin statistic, and that comes from the fact that the optimal weight matrix is just going to be Z prime, Z inverse, Z prime, and I've just put in some estimate of the standard error of the second stage regression, and then you get this Anderson-Rubin statistic out. Okay. There are a couple of other approaches, and I'm going to mention these. But I'm not actually going to recommend their use, and the reason is not so much that I think that they're necessarily bad ideas, although I'm not so sure I would endorse the LM version of it, because the LM has such strange properties in the linear model. It's more that these really haven't been particularly explored. So there's been very, very little study of in Monte Carlo situations or empirical experience working with these methods. There's an LM version of the GMM statistic that Kleibergen developed. There's a GMM version of the LM statistic that Kleibergen developed. There's a GMM version of the CLR statistic, a couple of those, one that we proposed, one that's in a paper by Kleibergen. There's some other methods that have been proposed, looking at so-called generalized empirical likelihood objective functions. So the generalized empirical likelihood objective function stuff, one of the main points of Guggenberger-Smith is when they use this weak identification asymptotics, they actually show that under weak identification, all these GEL tests are asymptotically equivalent to the CUE. So it's really not clear why you'd want to use any of these others. Maybe there's better performance in certain regards, but they're going to essentially have the same properties as the CUE objective function-based test, which is the nonlinear or GMM version of Anderson-Rubin. So I'm putting these slides up there. This is an active area of work. As you can see, these papers are all quite recent. I don't think that there's any. I don't think there's any clarity in terms of advice coming out of this at this point beyond what's on the previous slides here, which is using this GMM Anderson-Rubin. Okay. And I'll go through an example of that in a little bit. Okay. Mark did warn me that keeping you guys awake at 4:30 would be a challenge. So it's been a lot of work here. Okay. Talk a little bit about estimation. So I guess I told you my opinion about estimation in the linear model, which is that estimation as a theoretical matter is hard, and as a practical matter you get some goofy things in weak instruments. We've seen that in the GMM simulations in Hansen, Heat, and Yaron. So all of those opinions carry over to the to the situation in GMM. I guess there is something to be said if you want to do estimation. So the two-step is the GMM version of two-stage least-squares. We know for sure that two-stage least-squares is one of the worst things you can possibly do in the linear case. So that does suggest that two-step is probably not the greatest in GMM. Limmel will at least be inside this CUE or GMM Anderson-Rubin confidence set. So computing the Limmel estimator seems to be a plausible thing to do. You have to be prepared for some enormous outliers, however. So I don't think I have too much more to say about it. There's some interesting theoretical work in this paper here about and Monte Carlo stuff too, but interesting theoretical work. This is a very nice paper by Hausman by the MIT crowd on CUE. Although it's also been found to exhibit wide dispersion. Okay, as I mentioned, the so-called generalized empirical likelihood estimators are asymptotically equivalent to CUE under weak instruments. So I don't, at least to first order, don't see any particular reason why one needs to go down that road. So those are just some thoughts. This Fuller K-type thing is promising, but this is some unpublished paper that we just don't know too much about it yet. Okay, so let me try to get back to reality here, talking about some empirical application. Okay, so I'm going to look at the new Keynesian Phillips curve, and so this is great. Okay, so look, it says Gali and Gertler, Mavridis, misspelled, Nason and Smith. Okay, so 3 of those people are in this room. Well, let me talk about their work. Okay. So here's a new Keynesian Phillips curve with a lag in it, and then I've thrown on an error term which does or doesn't need to be there for these purposes. And so this is the moment, the rational expectations moment condition, and then here's the instrument set, which is with these additional lags, the t-1 dated, data. There's 2 included endogenous regressors. There's the expectational term here, what you're instrumenting for, and then there's the activity variable, whether that's an output gap or whatever. So there's 2 included endogenous regressors in this case. There's one so-called included exogenous regressor, which is part of the instrument set, which is the lagged value of inflation. And so in the terminology we have here, there's 2 included endogenous regressors, m equals 2. We will want to incorporate the possibility of say, heteroscedasticity. So this is not going to be a straight IV regression problem. And there's an interesting issue about potentially incorporating serial correlation as well. And so I'm not going to take a stand on whether you should or you shouldn't. That really depends on what you consider to be part of the model's primitives. But I will at least just talk about what those results look like. There's a very nice review paper, which is by Kleibergen and Mavridis, which goes over this and has references to most of the literature. So all I'm going to do is I'm going to show some exercises that a couple of people have done constructing Anderson-Rubin confidence sets in this model. And one of them is this paper by Dufour, Colleth, and Kitchian. And so the way they do this is they constructed this Anderson-Rubin confidence set. They constructed this Anderson-Rubin confidence set, I believe, by a grid search, which is why you see these bumpy regions in here. And it's the non-rejection region of the Anderson-Rubin statistic. And so then this is plotted. This is the thetas and omegas. So for the derivation of the new Keynesian Phillips curve, there's thetas and omegas, and then these gammas here are the functions of the thetas and omegas, and they're the things that actually appear. So I'll just focus on those. There's the gamma on the future value and the gamma on the the lagged value. And empirically, what they find is that it looks like you can't distinguish between what gamma and the two forward and lagged ones are, but they seem to add up to 1. So that's the empirical finding from looking at the Anderson-Rubin test. I think one thing that's worth noting is that these things are most certainly not ellipses. So if you were doing standard GMM and you wanted to construct a confidence set, you would take the point estimate and then you would draw that little ellipse around it. And so we even have, Mark and I have a textbook that has that picture, but this is not that picture. Okay, so this is the point estimate, and then this is certainly not the ellipse. All right, so that's actually the main. This looks a little bit more ellipsoidal, but it's probably, to numerical accuracy, kind of hard to tell. There's this. My understanding is that what these guys did is they did not hack this. That is to say, they did not take into account the possibility. They did not allow for any serial correlation in this orthogonality. In the error term, and so the error term is h times zt minus 1. So that should have conditional mean 0 given the past. So that means it should be serially uncorrelated. But the instruments are doubly lagged, so there could be an MA1 error that's introduced by the doubly lagged instruments. And if I understand it correctly, that's what Kleiberg and Mavridis did. I should actually look at, if I got this right? Good. That's what they took into account. And so that methodology, and this was also done, this was done by, was this done? No, this would have been done using a grid search also, right? On a finer grid. And so these are their confidence sets. They call these S sets, the terminology. This is just the nonlinear Anderson-Rubin confidence set. And so what you can see, again, this is in lambda and gamma F space. So it's unfortunately not the same space, gamma B and gamma F. It's lambda and gamma F space, where this is the forward value and this is the activity variable. And so the confidence set is clearly not ellipsoidal in either of these cases. How do you get, if you have a confidence set, well, you can get confidence intervals by projecting that set down to one axis or projecting it down to another axis, and that's what you can see in those in these calculations. So that's the Kleiberg and Mavridis example. And again, it's not like this is really bizarre, a bizarre set. It's kind of ellipsoidal, but it's not exactly ellipsoidal. But I mean, my take on it is that in the end, once these guys have figured out how to do this, this isn't that hard to do. And look, either you're going to get standard inference, in which case that's fine. It was just a robustness check, and you can put it in an appendix or a footnote, or you're going to get a different answer. And if you get a different answer, this is the answer to believe, not the GMM printout. Okay, so here's an example where identification is really weak, and this is just the nonlinear version of the Yogo problem. So again, a model maybe nobody really much believes, but it's an interesting one to look at, and certainly has played an important role in the literature historically. So we looked at some. Should be 2000. We looked at some annual data here with stock returns and bond returns, and then we did double lagging because of temporal aggregation concerns, using consumption growth and stock returns and bond returns as instruments. And so here's the sets that we got. So the gray region is the Anderson-Rubin confidence set, and so this is gamma and delta. Okay, so gamma is this exponent coefficient, and delta is the discount factor, and so the gray thing is the Anderson-Rubin nonlinear Anderson-Rubin confidence set. This is the confidence ellipse that's produced by the output from two-step optimal GMM. So there is no overlap, right? There's no overlap between the GMM confidence ellipse and the Anderson-Rubin confidence set. Now, you can't report this, right? This can't be what you would report. I mean, if you have these information, you can't dismiss this. I mean, it's possible as a matter of theory that these, in fact, if it's strong identification, this ellipse would be shaded gray. These two would overlap. They're completely unrelated to each other. But that's completely consistent with this weak instrument theory, that 2-stage least-squares just goes somewhere. It goes somewhere useless. And it produces standard errors that are just about as good as that 0.011 from Bound and Jaeger. Okay. Now let me talk a little bit about many instruments. I don't know. Let me see. Maybe I'm not clear enough. Two-step GMM is a really bad idea in this problem. Here is an example where fully robust weak instrument inference gives sensible and useful answers. Unfortunately, this gamma F doesn't seem to be very well determined, but that's because you've got weak instruments. It's correctly telling you what's in the data. Okay, so anyway, I just wanted to be clear. All right, let me talk about many instruments. Well, optimal GMM requires using the optimal instrument. Usually, optimal instruments are really reasonably complicated functions of the data. So in our settings, in time series settings, those optimal instruments probably include projections on the entire history, the optimal projection on some entire history of the data. Well, you can't implement that. You can only run a finite order autoregression or something like that, or in the first stage. But we can play a game. And the game we're going to play is that we're going to let the number of regressors that you include grow with the sample size. So you might say, a typical rate that you'll find, and we'll come back to this in a hack, a typical rate you might find would be something like, say, k cubed, or k is p cubed, which is the number of lags, over t tends to 0 or something like that. Or maybe it depends. I mean, you might get a square root or you might get a p to the 4th. It depends upon how you do the calculations. So the game then is more and more and more lags are always going to be adding just a little bit more to give you more efficiency. More lags is better. You're going to get a smaller omega. You're going to get more efficient instruments, bigger values of p. And that is incredibly misleading. Right? That whole literature, I think that just really takes you down the wrong road. Think about what I've been talking about with weak instruments. It's really hard to forecast consumption growth. Okay? How is it going to be better to say, so if I'm using this year's consumption to forecast consumption growth and this year's interest rates and this year's stock prices, how can it possibly be better for me to start adding last year's and the years before that and the year before that? I mean, that's only going to make the weak instrument problem worse. It's going to get you back into this Bound, Jaeger, Angress-Kruger problem where it was all right if they only used 3 instruments, but by the time they're using 178, they were cooked. Right? So if you're working, say, in a hypothetical example, estimating a new Keynesian Phillips curve using 4 variables and 6 lags, those like lags 2 through 6 are probably hurting you in terms of your in terms of your inference. They might be adding a little bit in some vague sense to non-centrality parameters, but they're making the distribution theory worse. Let me give you the example. All right, so I'm going to go back to this example. We did this at the beginning. This is beta hat, two-stage least squares. Remember how I did the weak instruments asymptotics converging to this object here. I don't know if you're... Anyway, I did this. We did this. You saw this. Okay? There's enough information in the slides that you could reproduce this. You can step by step. Okay? And then we did this projection. Remember I did the Cholesky decomposition of ZU and ZV? So I projected ZU on ZV, and I got this orthogonal residual. These are all asymptotically normal, so these are independent. Okay, so now I'm going to play a game. I'm going to take this expression here, and the game I'm going to play is I'm going to imagine that the number of instruments is getting bigger and bigger and bigger. And so now lambda has the dimension of the number of instruments. So it is Z sub V. All right, so it's the dimension of the number of instruments. So what's going to happen? So I'm going to say lambda is getting bigger and bigger, but on average, the amount of information per instrument is tending to a constant number. Okay, so I don't know. So what's lambda prime lambda? By the way, you know what lambda prime lambda is? Lambda prime lambda is equal to mu squared in this setup. All right? So lambda... I should have said that right a long time ago. The denominator is a non-central chi squared with non-centrality parameter lambda prime lambda. Lambda times lambda is mu squared. So I'm going to say mu squared on average. The average concentration parameter, the average information per instrument is converging to a number. It's not getting big, it's not going to zero. So I'm adding instruments, and each one, I'm adding a weak instrument. I'm not adding irrelevant instruments, because that would drive this to zero. All right? I'm not adding strong instruments, because that would drive it to infinity. I'm adding weak instruments. So I've got a list of weak instruments, and I'm going to play the game, add more and more and more what happens to the distribution. All right? So more and more weak instruments, and I add it to the distribution. Well, lambda prime ZV, now by a central limit theorem, this is just a non-random thing, prime normal divided by k by the central limit theorem. This is going to converge in probability to zero. Do you see this? It's so late. How can you do central limit theorem? Okay, so lambda prime ZV over k. All right, so what is that? That's 1 over k times the sum I running from 1 to k of zi v yes. Okay, so z times lambda I zv sub I. So zv is a k by 1 vector, and it's a normal. And so what am I doing? I'm taking these normals, I'm adding them up, and I'm dividing by k. And so what is this thing going to do? Well, it's going to converge in probability to zero because I'm dividing by k. All right? So that term, so actually, I'm going to get some nice simplifications. Weak instrument asymptotics, when I take it to a limit, many instrument asymptotics, or more precisely, many weak instrument asymptotics, gets rid of this term here. That's nice. And it gets rid of this outer term here, and it's going to get rid of this term, going to get rid of some other terms. It's going to keep this term, actually. It's going to get rid of this ZV-ZU term. Put it all together, and what do we have? Well, it turns out that if I let k tend to infinity, and I work everything out, I'm going to get this expression right here. Delta plus 1 over lambda sub infinity. But wait, we've seen that before. We saw that right here. So so it says that as k tends to infinity, beta hat 2-stage least squares minus converges in probability to beta naught plus delta over 1 plus the average amount of information per instrument. Well, what is it if the average amount of information per instrument is small? How about 0? 0 is an easy number to plug in. It's the p-lim of OLS. Isn't that amazing? So you can actually have a lot of weak instruments. Actually, if you have a lot of irrelevant instruments, it's going to converge in probability to the p-lim of OLS. Wait, that's exactly. That's exactly. So why did bound get exactly the number 0.081? Remember, I didn't really fully answer that. I just said Cauchy ratio messy, centered in the right place. But in fact, this converges in probability to 0 as k tends to infinity, and they had 178 instruments. So they actually got exactly the same thing. Well, use a lot of instruments and you don't have much information, you're basically going to be OLS. So, my takeaway from this is you should stay away from a lot of instruments. Other people have a different takeaway on this. And I think there's some validity to so this is I'll call this more of the MIT research program. And I understand, see, there's some beauty to this. Look at all these things that go to 0 when you have lots of instruments. You get this additional level of averaging, right? So instead of having just averaging in the sample size, we now have got an additional array of averaging in the number as the number of instruments gets large. And that's going to kill a lot of these problematic terms. So it turns out that if we imagine approximating a large instrument situation by k tending to infinity, that some of the real complications of the weak instrument problem actually disappear, and things become quite nice. You get some limiting normal distributions. There's bias, but sometimes you can even correct the bias. So that's what I call the MIT research program, which is essentially turning many weak instruments from a problem into a blessing. Okay, so now here's the rub. So it's a very interesting and intriguing research program. Let me talk a little bit about some things we know and some things we don't know. One thing we know for sure, so for those of you who are technical or sort of paying attention, trying to catch out the professor, this calculation was wrong. What did I do wrong in this calculation? I mean, technically, as a technical matter, I made a technical sleight of hand. I did sequential asymptotics. So I took a limit as t tends to infinity to give me this, fixing k. And then somehow I assumed that was uniformly good and I could let k go to infinity. And that's not right. It's not necessarily uniformly good. In fact, the condition that I need, the condition that I need for that uniformity is pathetic. It's k to the fourth over t tends to 0. That's not much worse than most of the conditions in this literature. And the reason is that there's a lot of really big nuisance parameters, like that z prime z matrix. Z prime z has to be controlled. But to estimate all of those terms in z prime z, right away you've got k squared terms. So all of those are going to have to be well behaved. So at a minimum, right off the bat, you can see you're going to need something like k squared over t going to 0. It turns out that things get worse than that, and you actually find a typical term to be like k cubed over t tending to 0. Weak instrument asymptotics is k tending to infinity, but k cubed over t tending to 0. So that's very slow infinities. All right, so what do we know? We do know some things. We know that under these very strong rate conditions, k is big but not too big, AR, LM, and CLR still work. CLR, it turns out you can prove some unbelievable results. You can actually prove that in this limit that the CLR is uniformly optimal. So that's not a proof that's often available. It's uniformly optimal among all tests in that limit. So it's really quite an astounding result. It's not necessarily so surprising because we know that it works extremely well along the sequence, but actually to be able to prove it in the limit is interesting. As a theoretical matter. In terms of estimation, you can exploit some of this. You can come up with bias adjustments and standard error adjustments, and that's these series of papers that are provided there. Let me give you my take on this literature. I think this is a really intriguing idea, and I think I think it's very intriguing, and there's potentially a lot to be gained from looking at these additional levels of smoothing or averaging that you get out of looking at many instruments. I worry a lot about this rate condition. And this rate condition does not seem to be something that's just there as an approximation. It really seems to play an important role. When you look at Monte Carlo performance, when K gets very big, really tends to deteriorate. As a practical matter, so if we look at 200 observations and 6 instruments, K cubed over T is 1. So I don't know if that's big or small or going to 0. If you look at the Ingres-Kruger, K cubed over T is 17. These look like moderately, I mean, I don't know, we don't have a metric for seeing whether that's big or small, but these look big enough to me to make me worry about really trusting some of the asymptotics that would be coming out of this many instrument literature. That said, I think that it's very promising, and there's some potential stuff that might be coming out of it, but I would think that this is not really, at this moment, ready for prime time in terms of trying to exploit the many instruments. So where that leaves me is in terms of practical advice, so there's 2 things. What do I give as advice to graduate students? The last hour has had about 3 or 4 PhD theses in it for sure to be written. As graduate students in econometrics. What do I give to graduate students in empirical macro? I'd say stay away from lots of instruments for the time being, at least until we understand it better, because what we do understand is they can really mess you up. All right? You can have seemingly precise inference around OLS. Okay, so how do you reduce the number of instruments? Well, there is this procedure by Donald and Newey, which is an information criterion method, and I think there's some applications in which that's probably not a bad idea. So if you can order the instruments, they have you do something. I'll talk about information criteria more, I guess, on Wednesday afternoon, but they have used an information criteria method that penalizes you for adding more instruments and looks at some amount of variance explained. What they can prove is that if you have some strong instruments and some irrelevant ones, you can prove that you're going to get only the strong ones. And that's a nice result. And that does suggest that if you have some strong ones and some weak ones, it's going to sort of drive you in the right direction. If you have all weak instruments, I don't think that none of their theory applies, and I don't think any of their theory would carry through to all weak instruments. It's not at all clear what the procedure would do in the entire weak instrument case, and I'm not sure that this would be the right way to approach it. But it might be useful, if you're saying, I've got my first set of lags, and I kind of think they're okay. Should I add second and third? That's maybe a useful tool. The other thing I guess I would just urge is, humility. Don't add lots of lags, and try to stay with a relatively small number of instruments. Okay. So, I guess a final comment here, and I probably said this about 100 times, is not to be fooled just because you run GMM, two-step GMM, and get small standard errors. Don't let that fool you. And there are an awful lot of techniques that are available and becoming available in the sites that are given here that I think are reasonably useful, at least as robustness checks or diagnostic checks. So that's it. Thanks very much.